These are the answers to the Chapter 19 packet, Chemical Thermodynamics. Section 19.1, Spontaneous Processes. If we take a look on page 786, it states that the first law of thermodynamics is that energy is conserved. In other words, energy is neither created nor destroyed in any process, whether that process is a brick falling, a candle burning, or an ice cube melting. Energy can be transferred between a system and the surroundings and can be converted from one form to another, but the total energy remains constant. So the delta E equation, where delta E equals Q plus W, delta E is the change in internal energy of a system, Q is the heat, and W is the work. So again, energy is conserved as the first law of thermodynamics. Delta E is the change in internal energy, Q is the heat, and W is the work. In this section, it goes on to say that a spontaneous process is one that proceeds on its own without any outside assistance. A spontaneous process occurs in one direction only. The reverse of any spontaneous process is always non-spontaneous. So in this particular question, we have to decide if each of the following processes would be spontaneous or non-spontaneous. So number one, is liquid water going to freeze on its own at negative 10 degrees Celsius? And the answer is yes, that's spontaneous. Number two, would the gas in flask B move all by itself into the flask A? No, that's not going to happen. That's non-spontaneous. Would liquid water spontaneously decompose into its elements? No, that doesn't happen. Would sodium chloride, if 1 gram of sodium chloride is added to 1 liter of water, would that spontaneously eventually form a solution in which the ions are broken up and aqueous? And the answer is yes. Now our next one's a little bit ambiguous. Is water going to change from a liquid to a gas at 100 degrees Celsius? Well, the problem is that you're exactly at 100 degrees Celsius. You're at equilibrium for that particular phase change, whether that's melting or boiling. So there is no preferred direction for the process if you're at the melting point or at the boiling point, because the two phases are in a state of equilibrium in which they are interconverting at the same rate. As we can see in figure 19.3, spontaneity can depend on temperature. So if the temperature is greater than 0 degrees, then ice melts. If the temperature is less than 0 degrees, then liquid water freezes. And if you're at 0 degrees, the two states are in equilibrium. It is important to understand that just because a process or a reaction is thermodynamically favored, it does not necessarily mean that it will occur at an observable rate. One example of a chemical reaction that is spontaneous at room temperature but normally takes a long time to occur is the conversion of iron into rust. Although the majority of spontaneous reactions are exothermic, so releasing energy, there are some spontaneous endothermic processes that do occur. Two examples are the melting of ice at room temperature, so that's endothermic, and the dissolution of solid ammonium nitrate. So if we take a look on pages 516 and 517, you can see that the dissolution of ammonium nitrate is endothermic. The delta H of solution is 26.4 kilojoules per mole. That's a positive delta H. And you can see an example of this application for an instant cold pack made from solid ammonium nitrate. When it's dissolved in water, the surrounding solution gets colder. And then a non-spontaneous process can occur only if the surroundings do work on the system. Section 19.2, Entropy and the second law of thermodynamics. Entropy is associated with the extent of randomness in a system. Entropy can also be associated with the extent to which energy is distributed among the various motions of the molecules in the system. The symbol delta H refers to the change in enthalpy. and delta S refers to the change in entropy. Note, you don't have to worry about equation 19.2 on page 790, and we're not going to do any calculations involving that equation. Here are some important bits of information from the AP Chemistry course and exam description regarding entropy. Entropy may be understood in qualitative terms. We can think about examples in which entropy is increasing, such as when matter is dispersed. So when a solid changes to a liquid or a liquid to a gas, the matter is dispersed in the sense that the individual particles become more free to move and generally occupy a larger volume. Entropy can also increase when a chemical reaction occurs in which there are a greater number of moles of product compared to reactant. Also, a gas, whenever it expands into a larger volume, entropy increases as the gas molecules can move within a larger space. So when matter is dispersed, as well as when energy is dispersed. So if we increase the temperature, then we disperse the energy because now there is a broader distribution of kinetic energies among the particles. So when temperature increases, entropy increases. All right, in this particular question, we have to predict the sign of delta H, so is it endothermic or exothermic, and then predict if entropy is increasing or decreasing. So melting is endothermic, and because a liquid is more random and spread out than a solid, entropy increases. Well, then the opposite of that, so freezing would be exothermic and would result in a decrease in entropy because you're going from a liquid to a solid, so the particles are becoming less random and spread out. They're more locked in place in the crystal. Evaporation is endothermic, and as you go from a liquid to a gas, entropy increases. But if a gas turns into a liquid, that's exothermic, and the entropy would have to decrease as the particles of gas change to a liquid. All right, next section, section 19.3, the molecular interpretation of entropy. So with respect to delta S, all you need to know is the following information. The entropy of the system increases, so a positive delta S, when the volume of a gas increases, so if a gas expands at constant temperature. If the temperature increases, entropy increases. If the number of molecules increase, as in you're doing a chemical reaction and you have, for example, 2 moles of product compared to 1 mole of reactant. If the state of matter changes from solid to liquid, liquid to solid, or solid to gas, entropy increases. If a solid crystal dissolves in a solvent to form a solution, then the particles are more spread out. Entropy increases. You don't have to worry about the Boltzmann equation or the concept of microstates. We're focusing on these qualitative descriptions of entropy in terms of that the particles are more spread out or more random. All right, according to the information in figure 1910, you can see that we have an ionic solid at the bottom of this picture, and now ions are breaking off and dissolving in solution. So the ions become more spread out and more disordered, so entropy increases for the ions. However, the water molecules are now becoming attached to these ions, so their entropy decreases as they're becoming more connected to these ions. So according to the information, the ions' entropy increases, but the entropy of the water molecules decreases. All right, let's go ahead and see if we can classify each of these changes in terms of delta S being positive or negative. Solid to liquid, more spread out, more random, entropy increases. Gas to liquid, now particles are losing some of their degrees of freedom. They're becoming more organized. So from a gas to a liquid, entropy decreases. A solid crystal now becoming aqueous, dissolved in water, more random, more spread out, entropy increases. If we go from 2 moles of gas to 1 mole of solid, we're losing our degrees of freedom. It's becoming less spread out, more ordered, so entropy decreases. And then finally going from 1 mole of gas to 2 moles of gas, more random, more spread out, entropy increases. According to the third law of thermodynamics, the entropy of a pure crystalline substance at absolute zero is equal to 0. Section 19.4, Entropy changes in chemical reactions. So in terms of this first example here, talking about entropy and temperature, take a look back on page 403. There was a diagram in which you can see 0 degrees Celsius versus 100 degrees Celsius. At 100 degrees Celsius, the molecules are moving faster and the distribution of speeds is more spread out. So on page 786, it says, an increase in temperature increases the most probable speed of the molecules and also broadens the distribution of speeds. Hence, the molecules have greater number of possible kinetic energies and the number of microstates increases. And we already know this, entropy of the system increases with increasing temperature. So curve B has higher entropy because it's at a higher temperature, the particles have higher average speed and a broader distribution of speeds. Entropy increases when energy is dispersed. Here we can see that going from a solid to a liquid to a gas, we increase the movement of the molecules. They become more random, more spread out, and that increases the entropy. So if we go from a solid to a liquid, there's a big jump in the entropy. And we go from a liquid to a gas, there's an even bigger increase in entropy. Even though the temperature is not changing, we are changing the phase. So liquid particles have more degrees of freedom and more entropy than solid particles. And gaseous particles have even more freedom to move around and spread out than liquid. So the entropy increases not only when the temperature goes up, but also during a phase change. All right, on page 801, as well as in the appendix that starts on page 1059, you can look up values for the standard molar entropy of various substances. Now, what are the units normally used for absolute entropy here? Well, you can see that the standard molar entropy has units of joules per mole Kelvin. The standard enthalpy of formation, so delta H of formation, and the standard entropy have a superscript 0. So what does that mean? It refers to standard conditions at 1 atmosphere and 25 degrees Celsius, or 298 Kelvin. All right, let's take a look at the difference between enthalpies of formation and entropies with respect to elements. So back on page 184, it says, by definition, the standard enthalpy of formation of the most stable form of any element is 0, because there is no formation reaction needed when the element is already in its standard state. However, on page 801, you can see many elements such as hydrogen, nitrogen, oxygen, lithium, sodium, etc., and yet their values for entropy is not listed as 0. So enthalpies of formation of elements are equal to 0, but standard molar entropies of elements are not equal to 0. In general, you would expect a gas to have greater entropy than the corresponding liquid or solid. And you would expect that in general, as the molecules get larger and more complex, entropy generally increases with the size of the molecule. On page 802, we have equation 19.8, which says that the delta S for a certain reaction would be equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. So on page 1059, so we are in Appendix C in the back of the book, you can find entropy values for calcium carbonate, calcium oxide, and carbon dioxide. So I'm just going to go ahead and write each of these entropy values underneath the chemical formula. Again, these are all in units of joules per mole Kelvin. There are no coefficients to worry about, so the delta S is simply 39.75 plus 213.6, so the products, minus the reactants, 92.88. And so we get positive 160.47 joules per Kelvin. The sign of delta S is positive, and this does make sense because we're starting with 1 mole of solid, and we end with 1 mole of solid and 1 mole of gas. We know that gases have a greater entropy than solids, so we know that the entropy for this chemical reaction must be increasing, so the sign of delta S should be positive. Now let's go ahead and calculate delta S for this reaction involving the synthesis of water vapor. So from page 1060 in the appendix, we have values of 130.58 for hydrogen, 205.0 for oxygen, and 188.83 for water vapor. Now to do the products minus reactants, we do have to take into account the coefficients. So our delta S is going to equal 2 times 188.83 minus the sum of the entropies for the reactants. That's the hydrogen, there's 2 moles of hydrogen and 1 mole of oxygen. If we do this math, we get negative 88.5 joules per Kelvin. So does the sign of delta S for this reaction make sense? On page 798, they're showing you an example where 3 moles of gas change to 2 moles of gas in the formation of nitrogen dioxide. The decrease in the number of molecules and the resultant decrease in motion result in fewer possible microstates and therefore a decrease in entropy. So, if we are going from 3 moles of gas to 2 moles of gas, we are reducing the degrees of freedom. Entropy is going to decrease, so the sign of delta S should be negative. And remember that we are not going to worry about equation 19.9 on page 803. We're not going to do any calculations with that. All right, our next section, section 19.5, Gibbs free energy. Remember that when ammonium nitrate dissolved in water, that was the instant cold pack example. That is a positive delta H for an endothermic reaction. Now the sign of delta S is positive because when the ions in the solid crystal dissolve in water, they have more freedom to move around. If you take some sodium metal and react it with chlorine gas, it produces sodium chloride. But that releases a tremendous amount of energy in forming sodium chloride. That's a negative delta H, a very exothermic reaction releasing a lot of heat and light. And the sign of delta S is negative because when you go from gas to solid, the particles have less freedom to move around, so they're more ordered and less random. All right, on page 804, we have equation 1912. This is the Gibbs free energy equation. Delta G is the Gibbs free energy equation. Delta G equals delta H minus T delta S. The sign of delta G can tell us if the reaction is going to occur or not, if it happens spontaneously or it is thermodynamically favored. If the delta G is negative, then it is spontaneous or favored in the forward direction from left to right. If delta G is 0, then you are at equilibrium. And if delta G is positive, then it is non-spontaneous. It's not favored in the forward direction. Work would have to be done to make that reaction occur. But since it's non-spontaneous in the forward direction, that means it must be spontaneous in the reverse direction. So in general, if a reaction is spontaneous, we can assume that the free energy must decrease for that reaction to happen all by itself. All right, it's a good time to talk about Q versus K. So we have 3 possible scenarios. Q is less than K, so we have too many reactants or not enough products. The reaction would proceed spontaneously toward the right until equilibrium is achieved. If Q is greater than K, now we have too many products or not enough reactants, it would proceed spontaneously toward the left. And if Q is equal to K, then you've already reached equilibrium. All right, here we have an example of using the Gibbs free energy equation. So delta G equals delta H minus T delta S. We're given a delta H, we're given a delta S, and because we're at standard conditions, temperature is 298 Kelvin. Now watch out for the units because we have negative 196.6 kilojoules, per mole of reaction. And we have negative 189 joules per mole Kelvin. Now again, that's per mole of reaction because we have different coefficients. All right, here's our delta G equals delta H minus T delta S. Let's plug in the numbers. Negative 196.6 kilojoules minus the temperature, 298 Kelvin. And look at what I've done here. I divided the entropy value by 1,000 so that I would have units of kilojoules per Kelvin. If I do this math, I get negative 140 kilojoules. So that particular reaction would be spontaneous or thermodynamically favored because we have a negative delta G. So the reaction is favored because the sign of delta G is negative. So now we're going to talk about driving forces. Which one of these quantities, the delta H or the delta S, is responsible for this reaction being spontaneous? Okay, what's the driving force? Well, would a negative delta S result in a negative delta G and therefore drive the reaction? No, because negative times the negative is a positive, so that would not help. A negative delta S means that the entropy is decreasing. That cannot drive the reaction. Well, what about a negative delta H? Well, that certainly can drive the reaction. So an exothermic reaction has a negative delta H, and that can cause delta G to be negative. So this reaction is driven by enthalpy only. It is not driven by entropy. All right, we have a different reaction. Again, this is the dissolution of ammonium nitrate in water. We have our delta H, we have our delta S. Here's the Gibbs free energy equation. Again, watch out for units. So again, I have a positive 1087 joules per Kelvin. I have divided that by 1,000, so I could get kilojoules per Kelvin. And if we do this math, we get negative 6.4. So again, it is favored thermodynamically because the sign of delta G is negative. So what is the driving force in this reaction? A positive delta H, would that drive the reaction giving a negative delta G? No. A positive delta H, that's an endothermic reaction, that cannot be the driving force. What about a positive delta S? Yes, a positive delta S, which is increasing entropy, that can be the driving force. So in this situation, the driving force is not enthalpy, but rather entropy. All right, so on page 806, we see the following equation. Delta G equals the sum of the free energy of formation for the products minus the sum of the free energy of formation of the reactants. Now, products minus reactants is a pretty easy calculation to do. We're going to do it for this equation involving the formation of sulfur trioxide. So on page 1061, we see that the delta G of formation for SO2, for oxygen, and for SO3 can be found. Of course, oxygen being an element, it has a free energy of formation of 0. Don't forget we have coefficients of 2 for the SO3 and for the SO2. So if we do the math, 2 times the number for SO3 minus 2 times the number for SO2 and then 0 for oxygen, we get negative 140 kilojoules for our delta G for that reaction. That number, negative 140 kilojoules, should look very familiar to you. We had gotten that number earlier in the packet. So it doesn't matter how you calculate delta G, we should get the same answer. All right, the following information comes from the AP Chemistry course and exam description. The phrase thermodynamically favored means that products are favored over reactants at equilibrium, so K is greater than 1. Historically, the term spontaneous has been used for delta G is less than 0, but that might be misleading because students might think that spontaneous means immediately or without cause. So the better phrase is thermodynamically favored. If delta H is negative, so it's exothermic, and delta S is positive, so entropy is increasing, there is no need to calculate the delta G. We know that the process is thermodynamically favored no matter what. That's the best case scenario when you have an exothermic reaction and entropy is increasing. Now, just because it's thermodynamically favored does not necessarily mean that it happens at a measurable rate. It might be very slow. Now, if instead of having a negative delta H, what if we have a positive delta H? That's endothermic. And what if the delta S is negative? That's the worst case scenario. So that the reaction would always have a positive delta G, so it's not thermodynamically favored. What does that mean? It means that K is less than 1. So we're not favoring the products, we're favoring the reactants. A good example of this would be perhaps a reaction that has a very small value of K, like a very, very weak acid. All right, in general, if delta G is positive, it is not favored. And if delta G is negative, it is thermodynamically favored. Okay, next section, 19.6, free energy and temperature. All right, so again, we talked about this. If delta H is negative and delta S is positive, then the sign of delta G must be negative, and this process would be thermodynamically favored at all temperatures. On the other hand, if delta H is positive and delta S is negative, then the sign of delta G must be positive. And this process would not be favored at any temperature. In fact, the reverse process would be favored. But what if we have situations where both delta H and delta S have the same sign? You can see this in the table on page 809. So, when delta H and delta S are both negative, it would be spontaneous at low temperatures, or favored at low temperatures, and not favored at high temperatures. On the other hand, if both delta H and delta S are positive, it would be favored at high temperatures, but not at low temperatures. Let's take a look at the equation and see why. If I have a negative delta H, but I have a negative delta S, if temperature is large, then that T delta S term, that negative T delta S term now becomes positive, and that might make the delta G overall positive. So it is favored at low temperatures, but it would not be favored at high temperatures. Eventually, if the temperature was high enough, delta G would become positive if the temperature was large enough. On the other hand, if delta H is positive and delta S is positive, it would be favored at high temperatures. So you want a negative delta G, therefore you want your temperature to be rather large. It would not be favored at low temperatures because, again, the positive delta H would probably make the overall delta G positive. So think about the math involved under these situations. For an endothermic reaction, you want high temperatures, but for an exothermic reaction, you want low temperatures. Well, here we have two different temperatures. We have 750 and we have 1250. This happens to be an exothermic reaction. Let's see what happens if we run this experiment at 750 Kelvin. So there's the calculation I'm doing for 750 Kelvin, and I get a delta G of negative 54.4. So it is favored. If I run this at a higher temperature, now when I plug in that 1250 Kelvin, look what happens. My delta G becomes positive. So it's favored at a lower temperature, but it's not favored at a higher temperature. Well, at what temperature would it switch over from being favored to not favored? In other words, if delta G is 0, that means that delta H equals T delta S. Let's go ahead and solve for the temperature at which it would achieve equilibrium. And if we do this math, paying attention to our sign and our units, we get 1037 Kelvin. So as long as the temperature is less than 1037 Kelvin, it should be favored. But once the temperature climbs above 1037 Kelvin, it would become not favored. All right, so for this next question, we're trying to go from liquid bromine to gaseous bromine. Let's figure out the delta H. That's just products minus reactants. Since bromine as a liquid is the natural state of bromine, its enthalpy of formation is 0. So we have a delta H of 30.71 kilojoules. For the entropy change, delta S, it's positive 93 joules per Kelvin if we do products minus reactants. All right, what do we do with delta H and delta S? Well, if we're going to use the Gibbs free energy equation, we can go ahead and solve for the temperature at which delta G would be 0. So we're going to use this to estimate the normal boiling point of bromine. So delta H divided by delta S, again paying attention to units here, is 330 Kelvin. Let's see if that answer is reasonable. We go back to page 429, which was in chapter 11, and sure enough, the boiling point of bromine is around 330 Kelvin, so that number is correct. All right, predict if the evaporation of bromine should be favored at 200 Kelvin. Well, not if the boiling point is 330. So since 200 Kelvin is below the normal boiling point, evaporation should not be thermodynamically favored to occur at 200 Kelvin. So when I plug in 200 Kelvin into the Gibbs free energy equation, I get a positive number. So a positive delta G means that the process is not favored at that particular temperature. Okay, section 19.7, free energy and the equilibrium constant. So we are given information about the reaction for the synthesis of ammonia. The value of delta H, which would be products minus reactants, that's 2 times negative 46.2 minus 0. So we have negative 92.4 kilojoules for our delta H. It's an exothermic reaction. The delta S, products minus reactants, so 2 times the number for ammonia, minus the sum of the entropies for both nitrogen and hydrogen. And that works out to be negative 198.3 joules per Kelvin. Now we're going to get the delta G by just using the Gibbs free energy equation. So that's going to be negative 92.4 minus, we're at standard conditions, so 298 Kelvin, multiplying that by the appropriate units. Notice I had to divide by 1,000 again, so negative 0.1983 kilojoules per Kelvin. And if I do this, I get negative 33.3 kilojoules. So that reaction is thermodynamically favored at 298 Kelvin. So this section has to do with the relationship between the free energy and the equilibrium constant. So on page 813, you can see an equation that relates the delta G with the equilibrium constant, capital K. So we're going to calculate the value of K for this reaction. Now to rearrange this equation, first I'm going to divide both sides by negative RT, and then I'm going to raise each side to the power using the exponent. So E raised to the negative delta G over RT is equal to K. Now the delta G, remember, was negative 33.3 kilojoules. And then what I've done here, because of the units, I have to match kilojoules with kilojoules, is I divided R, 8.314 joules per mole Kelvin, I divided that by 1,000. So I've also got a negative sign and another negative sign because of the delta G. So pay attention to sign, pay attention to units. So my value of K is E raised to the 13.44 power, and I got 6.9 times 10 to the 5th power. That's a rather large value of K, but that's consistent with this being a product-favored process. So a negative delta G should lead to a large value of K. If a reaction has a very small value of K, then it's reactant favored. If it has a delta G that's positive, that's reactant favored or non-spontaneous, not favored in the forward direction from left to right. But on the other hand, if you have a large value of K, product favored, and you have a negative delta G. So if it is thermodynamically favored, then the K is more than 1 or large. If it's not favored in that direction, in the forward direction, then K is very small. You can see this information on page 813. So look at the positive delta G, reactant favored, K is less than 1. And on the other side, negative delta G, product favored, K is more than 1. Remember, just because a reaction is thermodynamically favored does not tell us anything about the rate. So it's important to realize that the fact that a process is spontaneous does not necessarily mean it will occur at an observable rate. Thermodynamics tells us the direction and the extent of a reaction, but nothing about the speed. So these two reactions are both considered thermodynamically favored because the free energy is decreasing, but the reaction on the left looks like it's slow because it has a high activation energy. The one on the right is fast. But again, thermodynamics tells us nothing about the reaction rate. All right, this next section talks about what's called coupling, where you can have a reaction that's not thermodynamically favored, and you can couple it to another reaction that is favored, and then add those two reactions together. So here we have copper sulfide decomposing to give copper and sulfur. The problem is that the delta G is positive. So copper cannot be obtained directly from copper sulfide because of this reaction, since it is not thermodynamically favored. Again, a positive delta G. But if we couple this to the combustion of sulfur, so burning sulfur in oxygen, which has a negative delta G, then we can add these two equations together and get an overall delta G that becomes negative. So take a look on page 814, and you can see that the sum of these two reactions together, so copper sulfide plus oxygen to produce copper and sulfur dioxide, look at that delta G. The overall delta G is negative 214. So in essence, we have used the spontaneous or favored reaction of sulfur and oxygen to provide the free energy needed to extract the copper metal from the mineral. Here is some more information from the AP Chemistry course and exam description. Electricity may be used to cause a reaction that is not favored to occur, like charging a battery or electrolysis. You can also use light as a source of energy. So for example, we can use light to pull electrons off of an atom, or we can use light to convert carbon dioxide into glucose from photosynthesis. An unfavorable reaction can be made favorable by coupling it to a favorable reaction, such as the conversion of ATP to ADP in biological systems. In this context, coupling means that the process involves a series of reactions with common intermediates and that the overall delta G is negative. All right, we now have a bunch of data for sodium chloride and silver chloride, as well as the ions involved, and we're going to calculate the delta H and the delta S for the process of dissolution of sodium chloride and dissolution of silver chloride. So starting with the delta H for the sodium chloride reaction, so we have products minus reactants. That's going to be the number negative 240.1, which is for sodium ion, and then negative 167.2, which is the chloride ion, minus negative 410.9 for sodium chloride. If we do this math, we get positive 3.6 kilojoules. Now on to the delta H for the silver chloride reaction. So we take positive 105.9 for silver, negative 167.2 for chloride, minus negative 127.0 for silver chloride, and we get positive 65.7. So we've calculated the delta H values. Now let's calculate the delta S values. So for the sodium chloride reaction, 59 plus 56.5 minus 72.3 gives us positive 43.2 joules per Kelvin. And for the silver chloride reaction, the delta S, 73.9 plus 56.5 minus 96.1, we get a delta S of positive 34.3 joules per Kelvin. Now that we have delta H and delta S values, let's go ahead and do the Gibbs free energy equation delta G calculation. And again, watch out for units. So for the sodium chloride reaction, that's 3.6 kilojoules minus temperature, 298 Kelvin, times 0.0432 kilojoules per Kelvin, and this gives us a negative 9.3. So that reaction is thermodynamically favored at 298 Kelvin. If we do the calculation using the Gibbs free energy equation for the silver chloride reaction, we get positive 55.5. So it is not thermodynamically favored at 298 Kelvin. You already know that silver chloride generally tends to be one of our precipitates in chemistry, so it's not very soluble, and this positive delta G is consistent with that. Therefore, you would expect a K value that's larger than 1 for sodium chloride, and a K value that is smaller than 1 for silver chloride. Again, we're going to call it the KSP because that's what this is, the dissolution of the salt. So here is our calculation for sodium chloride, and we get a K value of 43. Again, that's using K equals E raised to the power, which is negative delta G divided by RT. Again, watch out for sign and watch out for units when doing this calculation. And now on to the value of K, KSP, for the silver chloride. We get an extremely small value, which again is consistent with a positive delta G. So therefore, sodium chloride is much more soluble in water than silver chloride. So based on those KSP values, sodium chloride is much more soluble than silver chloride, which I think we already knew that. All right. That is now the end of the Chapter 19 packet. I hope that those answers and explanations were helpful. Thanks for watching.